Welcome, friend. In this video, we'll explore 10 of the strangest quantum effects you've probably never heard of. Each one real, each one backed by physics, and all explained in a way that's gentle and easy to follow. So, if you're curious, tired, or just looking for something fascinating to fall asleep to, you're in the right place. Let's begin. Chapter 1. Why you can't freeze a quantum particle. Imagine standing in front of a door, watching someone walk toward it. Every few steps, you call out their name, causing them to pause briefly and glance at you. If you keep calling them over and over again, frequently enough, they'll never actually make it to the door. Not because they don't want to, but because they keep getting interrupted by your observations. In the strange world of quantum physics, something similar happens, not with people, but with particles. This phenomenon is called the quantum Zeno effect, and it's one of those rare concepts where the act of watching can stop motion entirely. Not metaphorically, literally. The more frequently you measure a quantum system, the more you can slow it down, even freeze it in place. Let's gently walk through this paradox together. To begin, picture a quantum particle in a box. This particle isn't like a marble or a pebble. It doesn't have a fixed location or state until you look at it. Instead, it exists in a state of possibility, a fuzzy cloud of maybes that evolves over time. If left alone, the particle will naturally evolve, changing states, perhaps decaying or tunneling through a barrier. This evolution is part of what's known in quantum mechanics as the Schrödinger equation, a mathematical expression that predicts how quantum systems change over time. But here's the twist. In quantum mechanics, measurement is a disruptive act. When you measure a quantum system, you force it to pick one of its many possible states. The act of observing it collapses its wave function from a spread-out set of probabilities into a single, definite outcome. Normally, this happens once, and then the particle continues evolving again. But what if you measure it again, and again, and again? What if you measured it so frequently, so repeatedly, that the particle never has time to evolve in between? This is where the quantum Zeno effect comes into play. It's named after Zeno of Elea, a Greek philosopher who famously proposed paradoxes about motion, such as the idea that a moving arrow is always at rest if observed at each instant. While Zeno was speaking philosophically, quantum mechanics has turned that metaphor into a real, measurable effect. Let's imagine a particle that's supposed to decay over time, say an unstable atom that will emit radiation and transform into another form. If you let it sit without disturbance, it will eventually decay according to well-established rules of quantum mechanics. But if you start measuring it very frequently, checking every nanosecond whether it is decayed, it turns out that you can delay its decay. In fact, if your measurements are rapid enough, you can prevent it from decaying entirely. The particle remains in its original state, frozen by your constant observations. Why does this happen? It's because of the way quantum systems evolve. Right after a measurement, the probability that the system has changed is extremely small. Mathematically, this probability grows quadratically with time at very short intervals. So, if you keep measuring before enough time has passed for a significant change to occur, you keep resetting the system back to its initial state, over and over, as if each observation resets the clock. It's a bit like trying to fall asleep but being nudged every few seconds. Each time your mind begins to drift off, you're pulled back to wakefulness. If the nudges are frequent enough, sleep never comes. Similarly, the quantum particle never gets a chance to evolve. This effect has been demonstrated experimentally. One of the first clear confirmations came in the 1990s when physicists used laser-cooled ions trapped in electromagnetic fields. They prepared the ions in a specific quantum state and showed that repeated observations prevented the ions from transitioning to other states. As expected, when left alone, the ions evolved. But under rapid measurement, the evolution stalled. It's a beautiful illustration of how quantum systems don't follow our classical intuitions. In the everyday world, looking at something doesn't stop it from moving. Watching a car doesn't stop it from rolling down the street. But at the quantum level, watching is interference. Measurement injects energy, resets probabilities, and fundamentally alters the evolution of a system. Now here's something even stranger. There's a flip side to this effect called the anti-Zeno effect, where under certain conditions, frequent measurements can actually speed up the decay of a system. It all depends on the nature of the interaction, the timing of the measurements, and the structure of the quantum environment. It's as if the universe sometimes decides that being watched is reason to hurry up, not slow down. This duality, Zeno and anti-Zeno, tells us something profound, that quantum systems are not passive. They respond to our attention, not metaphorically, but mathematically. In this world, knowledge has power, and observation has consequences. Let's pull back for a moment and reflect on the scale of this idea. The quantum Zeno effect isn't just a curiosity, it has implications for quantum computing, quantum control, and our philosophical understanding of time. In quantum computers, we rely on coherent evolution, systems that stay in delicate superpositions for as long as possible. But if those systems are disturbed or measured too often, their quantum behavior collapses. Understanding how to control or avoid Zeno-like effects is critical for building stable quantum technologies. There's also something quietly poetic about the effect. In a way, it tells us that change requires freedom. To let a quantum system evolve, you have to give it space. Not observe, not interfere. Let it breathe, and when you watch too closely, you take that away. You freeze it in a sort of stasis, trapped by your curiosity. That might remind us of more than just particles. In a broader sense, perhaps the quantum Zeno effect is a metaphor for human behavior. Too much scrutiny, too much measurement, too much pressure, and change becomes impossible. Growth stalls. We need periods of unobserved time to evolve. But back to physics. You might ask, can we use this effect in practical applications? The answer is yes. One promising field is quantum error correction. In quantum computers, we want to detect errors without collapsing the system. Careful timing of weak measurements, gentle, non-invasive checks, can help preserve the system while keeping it on track. In this context, we're not freezing the system outright, but using the principles behind the Zeno effect to guide and maintain its state. Another application lies in quantum control, where scientists attempt to steer systems precisely through a sequence of quantum states. By managing when and how measurements are made, researchers can nudge a system toward desired outcomes, effectively sculpting its evolution. So in short, the quantum Zeno effect isn't just a thought experiment. It's a tool, a puzzle, and a principle that continues to shape how we build and understand quantum technologies. And as you lie here, perhaps your mind drifting slowly towards sleep, remember this quiet fact. In the quantum world, the simple act of looking can stop time. That somewhere, far below the surface of your pillow, in the buzzing of atoms and the dance of electrons, there exists a universe where watching is power, and stillness is not the absence of motion, but the consequence of attention. And now maybe it's time to let go of observation. Let the particles drift, let the system evolve, and let yourself fall gently into rest. Chapter 2. How particles can jump through wall. At first glance, the idea of something passing through a wall might sound like science fiction, or at least like something that should require brute force or magic. In our everyday world, solid objects stop other solid objects. You can't walk through a brick wall, no matter how quietly or persistently you try. But in the realm of quantum mechanics, the rules shift in ways that challenge everything we take for granted. There, particles can do something extraordinary. They can tunnel through barriers, not climb over, not go around, through. even when, according to classical physics, they don't have enough energy to make it to the other side. This phenomenon is known as quantum tunneling, and while it might sound like a theoretical oddity, it's one of the most important and real quantum effects in nature. In fact, without it, the sun wouldn't shine. To understand this strange behavior, let's start with something familiar. Imagine you're riding a bike toward a hill. If you don't pedal hard enough, if your kinetic energy isn't greater than the height of the hill, you won't make it over. You'll roll back down, defeated by the incline. Particles in classical physics are just like that cyclist. If they don't have enough energy to climb over a potential barrier, they stop and reflect backward. End of story. But quantum particles aren't confined to this binary logic. They're not just point-like marbles with exact positions and velocities. Instead, they exist as wave functions, mathematical expressions that describe a spread of probabilities. When a particle encounters a barrier, its wave function doesn't simply stop, it leaks through. And if there's enough of that wave function on the other side, there's a chance, however small, that the particle will be found there as if it had tunneled right through the wall. The higher and wider the barrier, the less likely this is to happen. But the fact that it happens at all is astonishing. Let's slow down and think about what this means. A particle, say an electron, with insufficient energy to cross a region of space, can still appear on the other side. It doesn't break the laws of energy conservation. It's not borrowing energy to cheat its way through. It simply exists in a different framework, one where possibility matters more than certainty, and where outcomes are governed by amplitudes and probabilities rather than deterministic paths. Quantum tunneling has been confirmed in many ways, both theoretically and experimentally. One of the most profound examples comes from the heart of stars. Inside the sun, immense pressure and temperature cause protons, positively charged particles, to collide at great speeds. But even in those conditions, classical physics says they shouldn't get close enough to fuse because their positive charges repel each other like two magnets with the same pole. The energy barrier between them, known as the Coulomb barrier, is just too high. But thanks to quantum tunneling, there's a small but non-zero chance that protons can pass through this barrier and fuse, creating helium and releasing energy. That energy radiates outward and reaches us as sunlight. In a very real sense, every sunrise is a testament to the strangeness of quantum mechanics. Quantum tunneling is also responsible for modern technologies like the scanning tunneling microscope, which allows scientists to image individual atoms by measuring the tunneling current between a sharp tip and a surface. The device wouldn't work if electrons didn't occasionally tunnel through the gap between the tip and the material. Tunneling is also at the heart of semiconductors and transistors, the building blocks of all digital electronics. In flash memory, for instance, electrons tunnel through insulating barriers to store information. And in radioactive decay, certain unstable nuclei emit particles not because the particles are pushed out with enough energy, but because they tunnel through the nuclear potential barrier that would otherwise trap them inside. But perhaps the most mind-bending aspect of tunneling is how it relates to time. If a particle tunnels through a barrier, how long does it take? Does it speed up? Slow down? There have been experiments and theoretical debates suggesting that under certain conditions, tunneling could appear to happen faster than the speed of light. This doesn't violate Einstein's relativity, because no usable information or energy travels faster than light in these cases. But the fact that such questions even arise reveals how tunneling dances at the edge of our conceptual understanding of space and time. Let's come back to a gentler image. Imagine placing a ball into a bowl with steep sides. In the classical world, the ball will roll around at the bottom unless you give it enough energy to escape over the edge. In the quantum world, if you wait long enough, there's a chance the ball will simply appear outside the bowl, even though it never had enough energy to leave. It hasn't broken the rules, it's followed different ones. This is what makes quantum mechanics so deeply counterintuitive. It doesn't contradict classical physics, it extends it. At small scales, it replaces certainty with probability and predictable paths with wave-like possibilities. Yet tunneling isn't just weird, it's elegant. It shows us that reality is flexible, not brittle. That barriers, no matter how seemingly impenetrable, are never absolute. And here's something quietly poetic. Tunneling reminds us that progress isn't always linear. Sometimes things seem impossible, like there's not enough energy to get to the other side. But with time, patience, and persistence, reality itself may offer a path through. Not around, not over, through. Perhaps that's why tunneling has become a favorite metaphor beyond physics, in art, in literature, and in life. It's a reminder that what seems fixed may not be, that even the most solid wall is at its core made of probabilities and openness. And now, as you lie still, as the world quiets, you might picture those tiny particles, flickering in and out of possibility, waiting, watching, drifting across boundaries not by force but by chance, moving through the impossible, quietly, invisibly. And perhaps, just perhaps, it's time for you to do the same. Let go of the walls of thought, drift, tunnel softly from the waking world into sleep. Chapter 3. Why electrons don't follow the rules. Electrons are among the most familiar building blocks of matter. They orbit the nuclei of atoms, form chemical bonds, carry electrical current, and power virtually every piece of modern technology. For something so small and ubiquitous, you might expect we'd understand everything about it by now. But the truth is more nuanced. One of the most precisely measured properties in all of physics, the magnetic behavior of the electron, reveals that electrons don't quite behave as expected. This small irregularity has opened the door to some of the deepest insights into quantum theory and continues to challenge physicists even today. To understand what's unusual, we begin with a basic concept: electron spin. Spin is a quantum mechanical property intrinsic to the electron, similar to angular momentum, but with no direct classical counterpart. Along with this spin comes a magnetic moment, a measure of how strongly the electron behaves like a tiny magnet. Early quantum theory, developed in the 1920s and 30s, suggested a neat relationship between an electron's spin and its magnetic moment. According to the Dirac equation, an elegant framework that merged quantum mechanics with special relativity, this ratio, known as the G factor, should be exactly 2. But experimental physicists, probing this prediction with increasingly sensitive equipment, discovered something strange. The electron's G factor is not exactly 2, it's a little more. The difference is minuscule, but it's real. And it was one of the first hints that something deeper was going on. This discrepancy became known as the anomalous magnetic moment. It's not a flaw in the theory, but rather a feature of a more complete one. Quantum electrodynamics, or QED. QED is the quantum field theory that describes how light and matter interact. It's considered one of the most successful physical theories ever devised, not just for its accuracy, but for its ability to explain this anomaly down to astonishing levels of detail. So what causes the anomaly? In the world of QE, particles like electrons are never isolated. They exist within a sea of virtual activity. Even in what appears to be empty space, quantum fluctuations constantly create and annihilate pairs of particles. Electrons, positrons, photons, all for incredibly short periods of time. When an electron moves through this fluctuating field, it interacts with these virtual particles. These interactions slightly alter its path, energy, and magnetic properties. In essence, the electron is continuously exchanging virtual photons with itself and its surroundings. These corrections, though subtle, accumulate to produce a measurable shift in the electron's magnetic behavior. To calculate this anomaly, physicists use Feynman diagrams. These are pictorial representations of the different ways particles can interact, including paths where virtual particles appear and vanish, creating loops and chains of interactions. Each diagram corresponds to a mathematical expression that contributes a small amount to the overall prediction. At the simplest level, these diagrams are few and manageable, but for more precise predictions, the number of diagrams grows rapidly. Today's calculations involve thousands of such interactions. Evaluating them requires massive computational resources and a precise understanding of how the different contributions combine. Despite the complexity, the result matches the experimental measurements with stunning accuracy. How do we measure something so small? Physicists use a device called a penning trap. It combines magnetic and electric fields to hold a single electron in place for extended periods of time. By monitoring how the electron moves in the magnetic field, specifically how fast it rotates, they can determine its magnetic moment with extreme sensitivity. These experiments are conducted in ultra-cold, ultra-stable environments, shielded from any external disturbance. The electron's behavior is observed with such precision that even the tiniest deviations from theoretical predictions become apparent. And those deviations, however slight, have enormous implications. Because QED includes contributions from all known interactions in the standard model of particle physics, its predictions reflect the influence of every known particle. If the measured value of the electron's magnetic moment were to differ significantly from QED's prediction, it could signal the presence of new, unknown physics, particles or forces not accounted for in our current understanding. In recent years, much attention has turned to the muon, a heavier relative of the electron. Muons are unstable, lasting only a fraction of a second before decaying, but they share the same charge and spin. Because they are heavier, they are more sensitive to certain quantum effects, making them an excellent candidate for testing theoretical predictions. The muon G2 experiment, most recently conducted at Fermilab in the United States, measures the magnetic moment of muons in a circular storage ring. As the muons move through a precisely controlled magnetic field, their spins precess, wobble like a gyroscope, and the rate of that precession reveals their magnetic properties. The results show a possible deviation from the predicted value. It's not conclusive, but it's suggestive. If confirmed by further experiments and analysis, it could point to physics beyond the standard model. That means something we haven't seen, perhaps new particles or interactions, may be subtly influencing the muon's behavior. This would not only reshape our understanding of quantum field theory, but could provide clues about dark matter, unification of forces, or entirely new sectors of the universe. Returning to the electron, we can appreciate its importance not only in theory, but in practice. Its magnetic properties influence countless physical systems. In magnetic resonance imaging, MRI, the resonance of electrons and nuclei in magnetic fields allows for detailed images of internal anatomy. In spintronics, technologies exploit the spin of electrons to store and process information. In quantum computing, the manipulation of electron spin states, called qubits, is one of the leading approaches for building powerful, scalable machines. The electron's behavior also helps explain how materials conduct electricity, respond to light, and exhibit magnetism. Subtle changes in how electrons align or move under certain conditions can give rise to phenomena like superconductivity, quantum Hall effects, and topological states of matter. All of this rests on our understanding of the electron's most fundamental properties, including its spin and magnetic moment. And yet, that understanding remains incomplete. The measurement of the electron's anomalous magnetic moment continues to serve as one of the most sensitive tests of quantum theory ever devised. It's a benchmark, a standard against which the entire structure of modern physics can be evaluated. Even the tiniest deviation is a signal. It either confirms our best models or suggests that they are not quite right. And if they're not right, then we must dig deeper, ask harder questions, and refine our view of the universe. That is the scientific process, never finished, always reaching beyond. The story of the electron's magnetic moment is not just about a small number in a table of constants. It's a window into the quantum world, a glimpse at how invisible interactions shape the fabric of reality. It's about precision, persistence, and the remarkable ability of theory and experiment to come together in the pursuit of truth. And in that pursuit, even the smallest particles, ones we rarely think about, ones that pass through our bodies and technologies countless times a second, can become the key to unlocking nature's deepest secrets. Chapter 4. Why some materials only conduct electricity on the outside. When we think of materials that conduct electricity, we tend to imagine metals like copper, aluminum, or gold, shiny substances that allow electrons to move freely through their bulk. We wire our homes with them, coat circuits in them, and rely on them to make modern electronics work. Conversely, we think of insulators like rubber or glass as materials that resist the flow of electricity entirely, blocking any current from passing through. But in the strange and evolving field of quantum materials, this simple division, conductor versus insulator, has begun to blur. There exists a class of materials that, paradoxically, behave as insulators on the inside, yet conduct electricity only along their surfaces or edges. They are called topological insulators, and their behavior challenges traditional understanding while opening up possibilities for entirely new types of electronics. At first glance, a topological insulator doesn't appear unusual. You might hold a small crystal in your hand and test it with electrical probes. If you place the probes on the interior, you'll find that it resists current, just like any good insulator. But place those same probes along its outer surface, and the result is dramatically different. Current flows easily, efficiently, and with remarkable stability. Why does this happen? To answer that, we need to take a step back and look at what makes a material conductive in the first place. In conventional conductors, such as copper, the outermost electrons in atoms are free to move from one atom to another. These electrons are not bound tightly to any particular nucleus. Instead, they form a kind of electron sea that allows charge to flow when an electric field is applied. This is what gives rise to electrical current. In insulators, by contrast, the electrons are all locked into place. The energy levels available to electrons in these materials are fully occupied, and the next available energy state is too far away for them to jump to. As a result, even if an electric field is applied, the electrons can't move freely and current doesn't flow. In quantum physics, this difference is usually expressed in terms of band theory. Materials have structures known as valence bands and conduction bands. In conductors, the conduction band is partially filled, allowing electrons to move. In insulators, there's a large band gap between the valence band, where electrons live, and the conduction band, where they could move freely, and that gap is too wide for electrons to jump across easily. Topological insulators, however, occupy a fascinating in-between state. Their bulk, the interior of the material, behaves like an insulator with a full valence band and a large enough band gap to prevent conduction. But their surface states, the electronic states at the very edge or skin of the material, remain conductive. What causes this strange surface behavior? The answer lies in the quantum mechanical properties of electrons, especially spin and momentum, and in something known as topological order. To understand this, let's use an analogy. Imagine you're walking on a large flat field. No matter where you walk, the ground is smooth, level, and unchanging. This is like a conventional insulator. Electrons in the bulk have no preferred direction or special pathways. Now imagine walking around the edge of a circular island with steep cliffs. While the interior is inaccessible due to cliffs, a narrow trail wraps around the edge. You can walk along the boundary, even though the bulk is impassable. Topological insulators are like this island. The cliffs represent the band gap in the interior that prevents electron motion, while the trail around the edge represents special electronic states that are allowed to exist only at the boundary. But there's more to it than just location. The surface states of topological insulators are not just ordinary conductive pathways. They are protected by the material's topological properties. Topology in mathematics studies properties that remain unchanged under continuous deformation. A classic example is that a donut and a coffee mug with a handle are topologically equivalent. They both have one hole. You can stretch, twist, or bend a donut into a mug shape without cutting or tearing. This concept, abstract as it may seem, has profound implications in physics. In topological insulators, the quantum wave functions of electrons form patterns that cannot be continuously transformed into those of ordinary insulators without crossing a phase boundary, like ripping the hole out of a donut. These patterns, or topological invariants, create constraints that force certain electronic states to exist on the surface. This means that the conductive states at the surface of a topological insulator are robust. They are immune to many forms of disorder, such as impurities, cracks, or small defects in the material. Electrons traveling along the surface cannot easily be scattered backward, a process that normally leads to resistance in conventional conductors. This is due to a phenomenon called spin-momentum locking, where the direction an electron moves is tied to its spin orientation. To reverse direction, the electron would have to flip its spin, but the rules of quantum mechanics forbid this under most ordinary conditions. This robustness makes topological insulators highly attractive for a range of emerging technologies. For example, one area of research focuses on using topological materials in low-power electronics. Because the surface currents in these materials experience little to no scattering, they can carry charge with minimal energy loss. In principle, this could lead to circuits that generate less heat, consume less power, and operate more efficiently than traditional semiconductor devices. Another exciting avenue is quantum computing. Certain topological insulators are predicted to host exotic particles called Majorana fermions when placed in proximity to superconductors. These particles are their own antiparticles and could be used to build quantum bits that are far more stable against errors than current implementations. In this way, topology offers not just a new kind of material, but a potential new kind of logic altogether. But the implications of topological insulators aren't limited to future technologies. They've already influenced how we understand the electronic structure of materials in general. For much of the 20th century, materials science was largely concerned with local properties: what atoms are present, how they're bonded, what crystal structure they form. Topological materials introduced a new way of thinking. Now, the global properties of electronic wave functions matter too. How electrons behave across the entire material, not just at specific points, can determine whether surface conduction occurs. This shift in perspective has sparked the search for dozens of new quantum materials. Scientists now explore topological semimetals, Weyl fermion materials, and quantum spin liquids, all of which extend the ideas of topological behavior into new physical regimes. It's worth noting that the discovery of topological insulators wasn't accidental. Theoretical predictions laid the groundwork, showing that if certain symmetries, such as time reversal symmetry, were preserved in materials with strong spin-orbit coupling, then these exotic surface states should emerge. Experimentalists later confirmed these predictions, detecting surface conduction using techniques like angle-resolved photoemission spectroscopy and low-temperature transport measurements. Real-world examples of topological insulators include compounds like bismuth selenide and bismuth telluride. These materials are relatively simple to synthesize and have been the subject of intensive study. In laboratory settings, researchers have observed electrons flowing freely across their surfaces while being completely blocked in the bulk, verifying the topological nature of their conductive states. As understanding deepens, engineers and physicists alike are exploring how to integrate these materials into existing platforms. While challenges remain, such as fabricating devices that isolate surface conduction from bulk interference, the potential is vast. In conclusion, topological insulators demonstrate how deeply quantum physics can reshape our understanding of the materials around us. They show that even something as basic as electrical conduction can behave in ways that defy classical logic. These materials are insulators inside, yet conductors outside, thanks not to their composition, but to the topology of their quantum states. What once seemed like a contradiction is now a cornerstone of modern condensed matter physics. And as scientists continue to peel back the layers of these remarkable materials, we're reminded that the behavior of matter is governed not just by its ingredients, but by the hidden geometry of its invisible waves. Chapter 5. What happens when two people see different realities? One of the most unsettling questions in quantum mechanics isn't about particles, fields, or wave functions. It's about agreement, specifically whether two observers can agree on what's real. In classical physics, this was never a concern. If two people measure the same object, a baseball's speed, a pendulum's swing, they might get slightly different numbers, but they agree on the event itself. The ball was thrown. The pendulum moved. The reality is fixed and shared. But in quantum mechanics, the situation is more delicate. The act of measurement plays a central role, and the line between observer and system is not always so clear. This idea reaches a kind of philosophical and physical crescendo in a thought experiment known as Wigner's friend. Named after the physicist Eugene Wigner, who proposed it in 1961, the paradox asks a seemingly simple question. What if two people observe the same quantum system, but one of them is inside the system itself? Can they disagree about what happened? And if so, who's right? To understand the implications, we first need to revisit the peculiar nature of quantum measurement. In quantum theory, particles like electrons, atoms, or photons don't have definite properties until they're measured. Instead, they exist in superpositions, states where multiple outcomes coexist as probabilities. An electron can be here and there. A photon can be polarized vertically and horizontally. Only when a measurement is made does the system collapse into a single definite state. The famous Schrödinger's cat thought experiment illustrates this. A cat is placed in a sealed box with a quantum trigger that might or might not release poison. Until the box is opened, the cat is both alive and dead in a superposed state. But once observed, the cat is either clearly alive or clearly not. Wigner took this one step further. He imagined a sealed lab with an experiment inside, a simplified version of Schrödinger's box. Inside the lab is Wigner's friend, performing a quantum measurement, say on a photon's polarization. The friend opens the box, observes the outcome, and records it. To the friend, the photon's wave function collapses, and a definite result is obtained. But outside the lab, Wigner treats the entire lab, including the friend, the apparatus, and the measurement itself, as a single quantum system. From Wigner's point of view, the whole lab is still in a superposition. The friend is in a state of saw spin up and saw spin down, entangled with the measurement outcome. Here's the key conflict. The friend has seen a definite result. Wigner, however, describes the friend as existing in a superposed state. Two people, two observers, now describe the same event differently. For the friend, the wave function has collapsed. For Wigner, it hasn't. So who's right? To make this less abstract, let's bring in a real-world analogy. Imagine you and your friend are playing a card game. Your friend draws a card, peeks at it, and tells you it's the Queen of Hearts. From their perspective, the card is no longer a mystery. It has a definite value. But imagine that somehow you view the entire room through a magical lens that shows all possible states still entangled. From your viewpoint, your friend hasn't seen a specific card. They're in a state of having seen every possible card simultaneously. This may sound absurd, but in quantum mechanics, it's a natural consequence of treating observers as physical systems governed by the same laws as everything else. Wigner's thought experiment forces us to confront an uncomfortable possibility. There may not be a single objective reality that all observers agree on. To address this, physicists and philosophers have proposed different interpretations of quantum mechanics. Each offers a different resolution to the paradox. One approach is the Copenhagen interpretation, which suggests that wave function collapse is a real, physical event triggered by observation, but it doesn't define exactly when or how that collapse occurs. In this view, Wigner and his friend are simply using different frames of reference, and once they compare notes, they'll agree. The collapse occurs for both once communication happens. Another view comes from the many worlds interpretation, where every possible outcome of a quantum measurement actually happens in a branching universe. When Wigner's friend measures the photon, the universe splits, one where the photon is spin up, another where it's spin down. Wigner is still entangled with both branches until he opens the lab. There's no contradiction because both realities exist, just in different worlds. Then there's the relational interpretation, which asserts that quantum properties only exist relative to an observer. In this view, the friend's reality is different from Wigner's, and both are equally valid. Reality is not absolute, it's observer-dependent. Recent experiments have begun to test the foundations of Wigner's friend using entangled photons and advanced interferometry. In 2019, researchers at Heriot-Watt University in Edinburgh implemented a variant of the thought experiment using two pairs of entangled observers, tiny quantum friends represented by photon systems, and found that under certain assumptions, Wigner's friend scenarios cannot be explained by traditional assumptions of realism and locality. In simpler terms, these experiments suggest that if quantum mechanics is correct, and nearly every experiment supports that it is, then either objective facts don't exist, or different observers can witness different outcomes of the same event. This doesn't mean that science collapses into subjectivity. It means that measurement is a fundamentally active process, not a passive observation. The moment an outcome is observed, the system and the observer become entangled, and that entanglement shapes what is real from their perspective. To illustrate this with another analogy, consider a security camera and a burglar. When the burglar enters a room, the camera records them. From the camera's point of view, a burglar was clearly present. But now imagine a world where that same room is viewed by a second camera that didn't record anything, because, from its perspective, the burglary didn't happen yet. If cameras could be in quantum superpositions, these mismatched recordings might not be a technical glitch, but a quantum fact of nature. The implications of this are profound. First, it reframes how we think about objectivity in science. If observation plays an active role in creating the properties of what is observed, then measuring devices, observers, and systems cannot be cleanly separated. Second, it affects quantum computing and quantum communication. In quantum information theory, concepts like entanglement and coherence are deeply tied to how information is shared between observers. Understanding when and how measurements affect systems is critical to making quantum technologies reliable. Third, it opens questions about the role of consciousness. Wigner himself speculated, though this is not a majority view, that consciousness might play a special role in collapsing the wave function. While most modern physicists treat observers as physical systems without invoking consciousness, the line between system and observer remains blurry. So what really happens when two people see different realities? In quantum mechanics, they may both be right, within their own frame of reference. The act of measurement doesn't simply reveal a pre-existing fact. It helps define what the fact is, at least for the person doing the observing. Wigner's friend is more than a mental exercise. It's a gateway into the philosophical and physical foundations of quantum theory. It asks us not just what is real, but who decides what's real, and when. Perhaps the most remarkable lesson from all this is that reality in quantum mechanics is not a fixed background, but a dynamic, interactive process. Observers, systems, and measurements form a kind of dance where knowledge and outcomes are shaped together. As experiments grow more precise and more clever, we continue to test whether the assumptions we inherited from classical physics, like shared reality and independent facts, can hold in the quantum domain. And so far, the answer seems to be no. Instead, we are learning that quantum mechanics offers a richer, more flexible picture of reality, one that depends on perspective, one that allows for difference without contradiction, one where the boundary between inside and outside, observer and observed, is more fluid than we imagined. Chapter 6. How electrons make tiny loops in a magnetic field. In everyday experience, the behavior of electric charges in magnetic fields is fairly predictable. We know, for example, that when a charged particle like an electron moves through a magnetic field, it tends to curve, spiraling or looping depending on the field's strength and orientation. This idea lies at the heart of devices like cyclotrons and MRI scanners. But beneath that familiar, classical behavior lies a much more structured quantum mechanical world. At very small scales, electrons subjected to a magnetic field do not simply spiral in smooth curves. Instead, their motion becomes quantized, restricted to specific energy levels and circular orbits. This phenomenon is called Landau quantization, and it reveals just how deeply magnetic fields shape the quantum behavior of matter. Let's begin with the classical intuition, then see how quantum mechanics reshapes it. Imagine a marble rolling across a smooth tabletop. If you blow across the marble with a constant stream of air, analogous to applying a magnetic field, it will start to move in a curved path. If the tabletop were frictionless and the wind never stopped, the marble would follow an endless circular or spiral trajectory. Now replace the marble with an electron and the wind with a magnetic field. In classical physics, the electron feels a sideways force, called the Lorentz force, that continuously redirects its motion, causing it to travel in a circular path. This is why charged particles spiral along magnetic field lines in devices like cathode ray tubes or particle accelerators. So far, this is familiar territory, but now imagine shrinking the tabletop down to the atomic scale and the marble becomes a quantum object, a wave as much as a particle. Here, the smooth circular motion becomes something very different. Quantum mechanics tells us that particles can only occupy certain energy levels. These discrete steps are called Landau levels, and they arise naturally from solving the Schrödinger equation for an electron in a magnetic field. Instead of smoothly adjusting its radius or energy like a classical marble, the quantum electron jumps between allowed energy states. These Landau levels are evenly spaced in energy, and each level corresponds to a circular orbit of a specific size. The higher the magnetic field, the greater the energy separation between the levels, and the tighter the orbits become. Electrons in a strong magnetic field cannot sit wherever they please. They must choose from these allowed orbits, looping around invisible centers like celestial bodies locked into precise paths. What's more fascinating is that each Landau level isn't occupied by just one electron. A given level can host many electrons, and the number it can hold depends on the strength of the magnetic field and the size of the system. Once one level is full, electrons begin to fill the next one. This structured behavior has real, measurable consequences. In most materials, such effects are too subtle to observe under ordinary conditions. But in two-dimensional systems, such as extremely thin layers of semiconductors or graphene, the effect becomes dramatic. When placed in a strong perpendicular magnetic field, these flat systems reveal the quantization of electron energy as a series of sharp plateaus in conductivity. This leads us to the famous quantum Hall effect. Discovered in 1980 by Klaus von Klitzing, the quantum Hall effect showed that in a two-dimensional electron gas subjected to low temperatures and high magnetic fields, the electrical resistance doesn't vary continuously. Instead, it drops in discrete steps, specific quantized values. Each step corresponds to a different number of filled Landau levels. To put this in a more relatable analogy, imagine pouring water into a series of buckets lined up on a staircase. As you pour, each bucket fills in turn. There is no smooth overflow from one to the next. It's bucket by bucket. Similarly, as you increase the magnetic field or change the electron density, electrons fill up the Landau levels one by one, and the material's properties shift accordingly. What makes this even more astonishing is the precision of the effect. The quantized resistance values are so exact that they have become a standard of measurement, used to define the ohm with unmatched accuracy. The quantum Hall effect is one of the few places in physics where quantum theory touches reality in such a clean and countable way. But why do electrons form these tiny loops in the first place? At the heart of the matter is a principle known as gauge symmetry, which tells us that electrons don't respond to magnetic fields directly, but to a mathematical construct called the vector potential. This abstraction may sound obscure, but it's crucial to understanding how magnetic fields influence phase and curvature in quantum wave functions. When an electron enters a magnetic field, its wave function acquires a twist, a kind of curling geometry that causes it to move in circular patterns. Each allowed Landau level represents a distinct way that the electron's wave can curl and still satisfy the boundary conditions imposed by quantum theory. It's not just about circles, it's about topology. These loops are not fixed in place. They drift sideways in what's known as a cyclotron orbit, and in clean systems, electrons can execute these orbits without scattering. But in the presence of impurities or edges, things get more interesting. Electrons near the boundary of the material form what are called edge states, and these states are remarkably robust. Edge states flow in only one direction, determined by the magnetic field, and are immune to backscattering. That is, even if there's a defect or impurity, the electron doesn't reverse course. It simply keeps flowing forward. This one-way traffic is a hallmark of topological protection, and it's one reason why the quantum Hall effect is so stable and precise. Returning to real-life analogies, imagine electrons as cyclists on a narrow circular track with a strong wind blowing always from the side. No matter how many bumps or pebbles appear on the track, the wind keeps them moving forward. The structure of the field forces them into loops, and those loops lock them into a direction. In this framework, electrons no longer behave as independent particles bouncing through a material. They become part of a collective, quantized system governed by field geometry and topological constraints. These insights have led to discoveries of fractional quantum Hall effects, where electrons seem to behave as if they have fractional charge. These effects arise from strong interactions between electrons. Essentially, the loops begin to talk to one another, forming composite particles and even more exotic states of matter. Research into these phenomena has opened the door to quantum materials and topological phases that could be useful for robust quantum computing. The stability of these edge states, derived from Landau levels, makes them excellent candidates for encoding quantum information with reduced susceptibility to decoherence. In laboratories today, researchers use tools like scanning tunneling microscopes and cryogenic transport measurements to probe these tiny loops, visualizing electron behavior in unprecedented detail. By fine-tuning magnetic fields, temperatures, and material properties, scientists can map the formation and filling of Landau levels in real time. So while it may seem abstract, this idea of electrons making tiny loops, the reality is incredibly concrete. These loops govern the transport of charge in microchips, the quantization of resistance in standards laboratories, and even the frontiers of topological quantum computing. Electrons, when confined and coerced by magnetic fields, do not simply wander. They dance, orbit, and align themselves into beautiful circular patterns governed by the laws of quantum geometry. Each loop they make is a fingerprint of the field, a direct imprint of the invisible forces that shape their world. And in shaping theirs, they shape ours. Chapter 7. Why accelerating makes you see heat. In our everyday world, we don't usually associate acceleration with temperature. If you floor the gas pedal in a car, you feel pushed back into the seat, but you don't suddenly get warmer. Speed and heat in our classical experience belong to different categories. But in the realm of quantum field theory, where space, time, and energy intertwine in complex and surprising ways, acceleration does something deeply strange. It creates the perception of warmth, not metaphorically, but literally. This is the essence of the Unruh effect, a prediction that an observer accelerating through empty space will detect a warm bath of particles, while an inertial observer, one who isn't accelerating, detects nothing at all. Both observers are moving through the same vacuum. Yet to one, it remains cold and empty. To the other, it glows with heat. To understand why, we need to explore how quantum theory and relativity describe the vacuum, not as a simple void, but as a sea of fluctuating fields filled with potential activity. Let's begin with the nature of vacuum in quantum field theory. In classical physics, a vacuum is just empty space, no matter, no radiation, no temperature. But quantum mechanics tells us that empty space is never truly empty. Even in its lowest energy state, the vacuum contains quantum fluctuations, random, momentary shifts in energy that create pairs of virtual particles and antiparticles. These particles flicker into existence and then annihilate almost instantly, too brief to be detected under ordinary circumstances. These fluctuations are real. Their effects can be measured indirectly through phenomena like the Casimir effect, where two closely spaced metal plates attract each other due to changes in vacuum energy between them. They also contribute to the energy levels of atoms and the behavior of elementary particles. But here's where it gets even more interesting. Different observers don't always agree on what the vacuum is. This disagreement stems from how observers measure time and space. According to Einstein's theory of relativity, motion affects your experience of time. A moving clock ticks differently compared to one at rest. In general relativity, acceleration and gravity further influence how time is experienced. An accelerating observer sees the world differently from a stationary one, not just in terms of motion, but in how space and time themselves are stitched together. In 1976, Canadian physicist William Unruh showed that this difference in perspective extends to the perception of the quantum vacuum itself. His analysis revealed that an observer accelerating through space would perceive the vacuum not as empty, but as filled with particles in thermal equilibrium, a warm gas of radiation. The higher the acceleration, the higher the temperature they would perceive. This is not due to friction, air resistance, or any mechanical heating. It's purely a quantum relativistic effect. Let's visualize this with an analogy. Imagine you're sitting in a still lake. The water is calm, and beneath the surface, gentle ripples pass by in all directions, subtle and mostly invisible. Now imagine that you begin to paddle forward, accelerating steadily. As you do, the relative motion between you and the ripples changes. Some seem to bunch up ahead of you, others appear to stretch out behind. Your acceleration creates a new relationship with the waves. In quantum terms, those ripples are vacuum fluctuations. As you accelerate through them, the way they appear to you changes. They no longer seem random or symmetrical. Instead, they begin to resemble thermal radiation, like heat. In more technical language, the vacuum state for an inertial observer is not the same as the vacuum state for an accelerating observer. The transformation between the two states, known as a Bogol-Lyubov transformation, mixes what we would consider particle and non-particle states. For the accelerating observer, the result is a thermal spectrum. The Unruh temperature depends on the acceleration. For human-scale accelerations, like a rocket launch or a roller coaster, the temperature is far too low to be detected. But at enormous accelerations, the effect becomes more pronounced. Theoretically, if you could accelerate fast enough, you'd actually begin to feel warm, even in the cold vacuum of space. While the Unruh effect hasn't been directly observed in a laboratory, the required accelerations are currently out of reach. It remains a robust prediction of quantum field theory in curved spacetime, a field that also underpins our understanding of Hawking radiation. In fact, the Unruh effect and Hawking radiation are closely related. In 1974, Stephen Hawking showed that black holes aren't completely black. Due to quantum effects near the event horizon, black holes emit radiation, a phenomenon now known as Hawking radiation. This radiation arises because observers outside the black hole see a horizon beyond which information cannot return. To those observers, the vacuum appears to radiate, just as it does for an accelerating observer. The similarity is more than analogy, it's mathematical. The event horizon of a black hole plays a role similar to the Rindler horizon experienced by an accelerating observer. In both cases, certain regions of spacetime become inaccessible, and the structure of the quantum vacuum changes accordingly. Let's make this idea even more tangible. Suppose you're sitting quietly in a spaceship, drifting in deep space. There's no heat, no radiation, only the cold of the vacuum. Then you fire the engines and begin to accelerate. To an outside observer, the vacuum remains unchanged. But from your perspective inside the ship, things feel different. The sensors start to register particles where there were none before. A faint warmth begins to appear, not from the engines, but from the vacuum itself. That warmth is Unruh radiation. Of course, the effect is tiny. To produce a measurable temperature of just a single degree above absolute zero, you'd need accelerations billions of times stronger than what rockets can currently achieve. Still, the physics remains sound, and the Unruh effect is widely accepted as a theoretical consequence of merging quantum mechanics with relativity. Researchers have explored ways to observe the Unruh effect indirectly. Some proposals involve ultra-intense laser fields that could create equivalent conditions for electrons in a vacuum. Others suggest analog systems, such as sound waves in a fluid or electrical excitations in certain materials, where similar behavior might be mimicked and studied. Beyond observation, the Unruh effect has sparked discussions about the nature of reality itself. If acceleration changes your experience of what exists in the vacuum, what does that say about the concept of particles? Are particles real, or are they observer-dependent constructs, emerging only when we interact with fields in specific ways? According to many interpretations of quantum field theory, particles are not fundamental. Instead, they're excitations of underlying fields, ripples in a deep, continuous structure. The Unruh effect reinforces this view by showing that what counts as an excitation depends on how you move. It also tells us something subtle about energy and information. From the perspective of an inertial observer, the vacuum is a stable, lowest energy state. But to an accelerating observer, that same vacuum appears to contain energy. This discrepancy doesn't violate conservation laws, but it challenges the classical intuition that energy should be the same for all observers. In quantum field theory, the energy of a system is linked not just to its state, but to the observer's trajectory through spacetime. In practice, The Unruh effect may never affect your daily experience, but it plays a vital role in shaping the edge of what we understand about the universe. It teaches us that motion shapes measurement, and that even the simplest state, empty space, is more complex than it seems. At its core, the Unruh effect reveals how quantum theory and relativity reshape our notions of temperature, motion, and emptiness. It bridges the gap between high-energy physics and thermodynamics, suggesting that heat and acceleration are not as disconnected as we once thought. And it reminds us that perception in physics isn't passive. It's tied deeply to how we move, how we measure, and how we exist in space and time. Chapter 8. When moving forward still takes you backward. In classical mechanics, motion is intuitive. If an object is moving forward, its momentum is positive. If you throw a ball down a hallway, you expect it to continue moving in that direction unless something interferes. The direction of motion and the flow of probability are one and the same. There's a comforting consistency in knowing that momentum and movement line up. But quantum mechanics doesn't always play by those rules. It allows for behavior that would be unthinkable in the classical world, like a particle that has only forward momentum, yet has a probability current that flows backward. This phenomenon is known as quantum backflow, and it stands as one of the most counterintuitive predictions of quantum theory. To fully appreciate why this is so strange and so beautiful, we need to first clarify what it means for something to flow backward in quantum terms. Let's begin with an everyday analogy. Imagine watching a group of runners all heading down a track. You clock their speeds and confirm that every one of them is moving forward. But strangely, as you tally how many runners pass a specific point over time, you notice something bizarre. Fewer runners pass by than you expect. Some seem to hesitate, slow down, or even drift the other way, despite all of them having forward velocity. This would make no sense in classical terms. Yet in quantum mechanics, something very much like this can happen, not with runners, but with probability. In quantum mechanics, particles are described not just as objects with position and momentum, but as wave functions, complex mathematical entities that encode the probabilities of finding the particle at different locations. These wave functions evolve according to the Schrödinger equation, and their structure determines how probability flows through space. In simple terms, if a quantum particle has positive momentum, meaning its momentum distribution includes only forward-moving components, you would expect its probability of being found in any point ahead of its current position to steadily increase over time. But in certain situations, that's not what happens. Quantum backflow refers to the effect where the probability of finding a particle in a given region of space decreases, even though all the momentum components of its wave function are pointing in the opposite direction. That is, even though the particle is moving forward, part of its probability seems to flow backward. It's not that the particle physically moves backward. The effect is more subtle. The probability current, which represents the flow of likelihood, behaves in a way that would be impossible under classical rules. The particle's wave function creates interference patterns that push probability in the direction opposite to the momentum. The existence of quantum backflow was first demonstrated theoretically in the 1960s and formally named and studied in the 1970s. It's not merely a mathematical quirk. It's a fundamental consequence of the way probability and momentum interact in quantum systems. To help visualize this, imagine water flowing through a pipe. In classical terms, if all the water is moving from left to right, you expect the total volume to shift in that direction over time. But in the quantum case, the water is a wave, and waves can interfere. If you superimpose just the right kinds of waves, you can create regions where the flow momentarily reverses, where, despite the overall motion being to the right, a temporary pulse of water moves to the left. This is what happens in quantum backflow. The wave function, despite containing only positive momenta, interferes with itself in such a way that the local probability flows backward. It's not a violation of any physical law, it's a direct result of the mathematics of quantum interference. One of the most remarkable aspects of quantum backflow is that it doesn't require exotic particles or strange boundary conditions. It can occur for a simple, one-dimensional free particle, a system as basic as quantum mechanics allows. All it takes is the right combination of momentum components and phase relationships. And yet, for all its simplicity, quantum backflow has never been observed directly in a laboratory. Why? Because the effect is very small. The amount of probability that flows backward is bounded. In fact, there's a universal limit on how much backflow can occur for a particle with purely positive momentum. This maximum fraction, known as the backflow constant, is less than 4%. That is, at most about 4% of the probability can flow the wrong way under ideal conditions. This makes the effect difficult to detect experimentally, especially in systems dominated by noise or decoherence. But that hasn't stopped researchers from trying. Various proposals have been made to observe quantum backflow using cold atoms, neutron interferometry, or Bose-Einstein condensates. These systems allow for the fine control of wave functions and momenta required to create the precise interference patterns that produce backflow. As experimental techniques continue to improve, it's likely that a direct observation of quantum backflow is not far off. Why should we care? Aside from the sheer curiosity of the effect, quantum backflow offers insights into the non-classical nature of quantum probability. It shows that probability in quantum mechanics is not simply about counting outcomes. It's a fluid, dynamic quantity that can exhibit interference and flow in counterintuitive ways. This challenges our classical intuitions about motion and causality. In classical mechanics, you can trace an object's trajectory from point A to B without ambiguity. In quantum mechanics, motion is governed by the evolution of probability amplitudes, and even the direction of that motion can be obscured by interference. In fact, backflow highlights one of the core differences between classical and quantum theories: non-commutativity. In quantum mechanics, position and momentum don't commute. That is, the order in which you measure them matters. This lack of commutativity leads directly to the uncertainty principle and underpins effects like backflow. From a practical standpoint, understanding quantum backflow may have implications in quantum control and quantum information. If we can manipulate probability currents at a fine level, we might develop new methods for steering quantum states or reducing noise in quantum computing systems. It also contributes to our understanding of arrival times in quantum systems. In classical physics, you can define the time at which a particle reaches a particular location simply by solving its equations of motion. But in quantum mechanics, particles don't have well-defined trajectories. Defining a quantum arrival time is much more subtle, and backflow shows that even with forward momentum, the probability of being ahead can decrease over time. This has sparked philosophical debates about the meaning of time, causality, and determinism in quantum theory. It also raises questions about how best to define time-dependent observables, quantities that don't have simple operator equivalents in quantum mechanics. Despite its elusive nature, quantum backflow continues to fascinate theorists and experimentalists alike. Its elegance lies in its contradiction: forward motion with backward flow. It forces us to let go of simplistic analogies and embrace the wave-like nature of quantum reality. It invites us to think not just about where a particle is or where it's going, but about how the probability of finding it evolves, and how even that can behave in ways we don't expect. As our tools for probing quantum systems grow more refined, we will likely see quantum backflow move from theory to experiment, joining the ranks of once paradoxical predictions like quantum tunneling and entanglement that became essential parts of modern physics. For now, though, it remains a reminder of the subtlety of the quantum world. Even when everything points forward, sometimes part of the system still looks back. Chapter 9. How particles feel forces from nowhere. In the classical world, a particle only responds to forces it directly encounters. A charged object accelerates in the presence of an electric field. A magnet pulls on iron filings within its reach. When we think about how something moves or changes course, we usually ask what field or force acted upon it. But in quantum mechanics, that relationship becomes more subtle. There exists a phenomenon in which particles change their behavior, not because they pass through a region with a force, but because they could have. They are affected by the presence of a field, even when they never directly touch it. The field, it turns out, doesn't need to apply a force at all. Just the possibility of a force existing somewhere nearby is enough to shift the outcome. This is the essence of the Aharonov-Bohm effect, a quantum phenomenon that reveals the deep and sometimes hidden influence of electromagnetic potentials on particles. It's a stark demonstration that in quantum theory, it's not only the fields we can measure that matter, but the potentials that underlie them. To grasp why this is so surprising, we need to understand how classical physics and quantum physics describe electromagnetic forces. In classical physics, electric and magnetic fields are the primary tools for describing electromagnetic interactions. The electric field tells us how charges push or pull on each other. The magnetic field describes how moving charges curve in space. These fields are real, measurable, and they exert tangible forces on particles. Underneath these fields, however, are potentials, the scalar electric potential and the vector magnetic potential. These are mathematical tools used to calculate fields, but in classical theory, they have no physical significance on their own. They're simply convenient devices for solving Maxwell's equations. But in quantum mechanics, things work differently. Particles in quantum theory are described by wave functions, and these wave functions are sensitive not just to local fields, but to the structure of space itself, including the electromagnetic potentials. Specifically, the wave function acquires a phase as it moves through space, and this phase can be altered by the presence of a potential, even if the corresponding field is zero in the region the particle travels through. Let's take a real-world analogy to illustrate what this means. Imagine you're walking along a circular path around a hill. The path is flat, and there's no slope. You don't gain or lose elevation as you walk. But if someone asks you how far you've walked, and you describe your path relative to the summit in the center, your answer depends on more than just your local steps. Even though you never climb the hill, the fact that it exists in the middle affects how your movement is described on a global scale. In the Aharonov-Bohm effect, the hill is a region containing magnetic flux, an area with a magnetic field, while the circular path is the trajectory of a charged particle, like an electron, which never actually enters the field-containing region. The remarkable prediction is that the wave function of the electron is still altered by the presence of that magnetic flux, even though the electron never encounters any magnetic field directly. To test this, physicists use a setup involving electron interference. The most famous version of the experiment is based on a modified double-slit arrangement. An electron beam is split into two paths that go around opposite sides of a region containing magnetic flux, usually confined inside a long, thin solenoid. The key is that the solenoid is completely shielded, so no magnetic field leaks into the regions the electrons travel through. From a classical standpoint, the electrons should behave as if the solenoid isn't there. But when the electrons are recombined on a screen, the interference pattern they produce is shifted. The wave function has acquired a phase difference between the two paths, depending on the total magnetic flux enclosed, even though no force ever acted on the electrons. The phase shift observed in this experiment is not arbitrary. It's directly proportional to the magnetic flux inside the solenoid. This shift cannot be explained by any local interaction with fields. It reveals that the electromagnetic potentials themselves are physically meaningful, not just mathematical tools. This is a major departure from classical thinking. In quantum mechanics, the phase of a wave function can interfere constructively or destructively with itself. That interference determines the likelihood of where a particle is found. A tiny change in phase, induced by a potential, can cause the particle to appear in a completely different place when measured. So even though the force was absent, the effect was real. It's like sending two identical waves across a pond that meet on the other side. If their crests align, they add up. If the crest of one meets the trough of the other, they cancel out. Now imagine that the pattern of ripples is altered just by the presence of an island in the middle. Even if the waves never touch it, the island changes the context of the wave's travel, and that context matters. There are both magnetic and electric versions of the Aharonov-Bohm effect. In the electric case, a charged particle can be influenced by a time-varying electric potential in a region where the electric field is zero. These effects are harder to observe experimentally, but they are predicted with the same confidence. To this day, the Aharonov effect is studied as a cornerstone of topological quantum physics. It is one of the simplest examples of how global properties, like the total flux enclosed by a path, can determine physical behavior, even when the local conditions seem irrelevant. This effect has implications in areas ranging from quantum computing to nanotechnology. In mesoscopic systems, structures only slightly larger than atoms, quantum coherence is preserved over long distances. In these systems, interference effects like the Aharonov-Bohm phase become essential for understanding how electrons flow. For example, in ring-shaped quantum dots, the conductance can oscillate as a function of enclosed magnetic flux. This is known as Aharonov-Bohm oscillation, and it's used to study coherence, phase shifts, and electron interactions in real devices. It also contributes to our understanding of gauge theory, the framework that underlies much of modern physics, including the Standard Model of particle physics. Gauge theory is built on the idea that different observers can describe the same physical situation using different mathematical potentials. The Aharonov-Bohm effect tells us that even if those potentials are gauged away in classical physics, they leave a physical fingerprint in quantum systems. What does this teach us? At the most fundamental level, the Aharonov-Bohm effect reminds us that context matters. A particle doesn't just respond to what it touches, but to the entire configuration of space it moves through. The structure of the wave function reflects not just immediate interactions, but global constraints imposed by the geometry of fields and potentials. It challenges the Newtonian idea that forces cause motion. Instead, motion is shaped by phase, and phase is influenced by potential, even when force is absent. This distinction between fields and potentials, local and global effects, is not just philosophical. It plays out in real experiments, affects real measurements, and informs how we design everything from sensors to quantum logic gates. In closing, the Aharonov-Bohm effect shows us that in quantum mechanics, what could have happened matters, even if it didn't. A particle can feel the influence of a force that never touched it. A trajectory can be bent by a presence that exerts no pull. And space itself, shaped invisibly by potentials, becomes an active participant in the behavior of matter. The forces of nowhere, it turns out, are very real. Chapter 10. When light bounces so fast, it makes matter. At first glance, it seems impossible. How could motion, mere acceleration or vibration, cause light to emerge from nothing? How could empty space suddenly produce particles just because something moves quickly enough? Yet this is precisely what the dynamical Casimir effect predicts. When a mirror accelerates through a vacuum at extraordinary speeds, it can give rise to real, detectable photons. Light born from motion, matter conjured from emptiness. To understand this, we must revisit one of the strangest and most fundamental aspects of quantum field theory. The vacuum is not empty. In classical physics, a vacuum is the absence of everything. No particles, no light, no sound, no fields. But in quantum mechanics, the vacuum is a dynamic, active state full of potential. Even in its lowest energy state, it buzzes with quantum fluctuations. Temporary, spontaneous disturbances in fields that briefly give rise to pairs of virtual particles. These virtual particles are not directly observable, but their effects are real. One of the most famous consequences of vacuum fluctuations is the Casimir effect, first predicted in 1948 by Dutch physicist Hendrik Casimir. Imagine placing two uncharged, perfectly conducting metal plates very close to each other, just a few nanometers apart. Quantum field theory tells us that virtual particles, especially photons, exist everywhere in space. But between the plates, not all wavelengths can exist due to the boundary conditions imposed by the metallic surfaces. Only certain standing wave modes are allowed. Outside the plates, however, all possible wavelengths can exist. This imbalance in allowed vacuum fluctuations creates a pressure that pushes the plates together. The plates attract, not because of any classical force, but because the quantum vacuum itself behaves differently inside and outside the gap. This is the static Casimir effect. It's subtle, but measurable. It has been confirmed experimentally many times, and it plays a role in the design of nanoscale machines, where Casimir forces can cause tiny components to stick together. Now, let's extend this idea. What if instead of stationary plates, you had a mirror that moves very fast, perhaps oscillating back and forth at a high frequency? According to quantum field theory, if the boundary that defines allowed vacuum modes changes with time, it can affect the structure of the vacuum itself. Specifically, it can transform virtual particles, those ephemeral quantum fluctuations, into real photons. Energy pulled out of what appeared to be nothing simply because the boundary moved. This is the dynamical Casimir effect. Let's use a real-world analogy to help make sense of it. Picture a child holding a jump rope that's tied at one end. If they shake the rope slowly, gentle waves travel along it. But if they shake the rope quickly and with precise rhythm, they can build up standing waves, ripples that grow stronger and more defined. Now imagine that the rope is the electromagnetic field, and the shaking hand is a mirror moving rapidly in space. The motion changes the conditions that the field must satisfy. If the motion is rapid enough, especially if it matches resonant frequencies, it can amplify vacuum fluctuations and convert them into real radiation, waves of light, generated by motion alone. In theory, to produce a detectable number of photons via the dynamical Casimir effect, the mirror would need to move at a significant fraction of the speed of light, an incredibly difficult task for any mechanical object. However, researchers have found ingenious ways around this. In 2011, a team at Chalmers University of Technology in Sweden performed a breakthrough experiment. Instead of using a physical mirror, they used a device called a superconducting quantum interference device, SQUID, a sensitive, tunable element that behaves like a mirror for microwave photons. By rapidly changing the electrical properties of the SQUID, they effectively created a boundary that moved at relativistic speeds. And when they did, they detected microwave photons emerging from the vacuum, photons that had no classical origin. This was the first experimental evidence of the dynamical Casimir effect. It showed that vacuum fluctuations are not just theoretical curiosities. They can be harnessed, manipulated, and transformed into something real. What's remarkable is that this phenomenon doesn't violate any conservation laws. The energy for the created photons comes from the motion of the mirror. By pumping energy into the system through acceleration or modulation, you allow the vacuum to borrow that energy and turn virtual particles into real ones. Nothing is created from truly nothing. It's drawn from the interaction between motion and quantum fields. This leads to a deep and fascinating insight. Motion through a vacuum is not passive. Accelerating boundaries change the structure of the vacuum. The vacuum becomes an active partner, responding to how space and time are altered by movement. Let's return to analogy once more. Imagine you're in a perfectly silent concert hall. No musicians, no instruments, no audience, just silence. But the stage itself begins to pulse, moving rhythmically, vibrating at just the right frequency. Suddenly, sound appears, not from any instrument, but from the architecture of the hall itself. The silence was not truly empty. It held the potential for resonance. All it took was the right motion to bring that resonance into reality. The dynamical Casimir effect is similar, except the hall is the vacuum and the sound is light. This effect has implications beyond pure curiosity. It informs our understanding of quantum radiation, field quantization, and the interaction between moving bodies and quantum fields. It's also closely related to phenomena like Hawking radiation from black holes and Unruh radiation, both of which involve particle production due to acceleration or the presence of an event horizon. In essence, these effects are different expressions of the same principle. The vacuum is observer-dependent. What appears as empty to one observer may be full of radiation to another, depending on their state of motion or the presence of a boundary. The dynamical Casimir effect also contributes to the emerging field of quantum thermodynamics, where researchers study how energy, entropy, and information behave at quantum scales. Systems that exploit vacuum fluctuations could, in principle, be used in quantum heat engines or energy harvesting devices that work by modulating boundaries instead of applying conventional forces. In quantum computing, understanding how motion and fluctuations interact is essential for building systems that maintain coherence. The fragile quantum property that allows superpositions and entanglement to persist. Any unwanted motion or boundary shifts could introduce photons from the vacuum, adding noise and degrading performance. In this context, the dynamical Casimir effect is both a potential resource and a design constraint. There's also something deeply poetic about the whole concept. We are used to thinking of light as a thing emitted by sources, a bulb, a star, an electron changing energy levels. But here, light is born from the boundary between possibility and movement. It is not emitted, but drawn out of the structure of space-time itself, catalyzed by motion. It reminds us that in the quantum world, energy can emerge from silence, light from shadow, action from what appears inert. The boundaries we impose, be they mirrors, conductors, or simply limits in space, are not neutral. They shape what the vacuum can and cannot do. And when we move those boundaries fast enough, we stir the vacuum, we awaken it. Thanks for spending this quiet moment with the universe. If you're still awake, there's another journey waiting for you. Just check the video description for more sleep-inducing science. And if you've already drifted off, sweet dreams among the stars.